Hi there. Welcome to a video lecture for Apply Math, Math 348. Today I am going to finish up some odds and ends from Legendre's equation, and there's another video already where I'm just writing down a Maclaurin series, and I did part of it on the board in class, and I'll try to finish it up here. So let's get started. All right. In a previous video, I spent some time writing down a power series expression for f of x equals this natural log 1 plus x over 1 minus x. And hopefully you've already watched that. And I just added to this particular note. So just to remind you, here's where we got. And now I am going to go on to the next piece of the puzzle, which is, let's go back and look at Legendre's equation. We solved this guy in class for particular initial conditions, as you see here. And what we got was y of x equals 3x. We used a power series to do that. So now I just want to step back a little bit and observe then that if that is our solution to that particular initial value problem, you can go ahead, you should verify this on your own. Take the time, stop the video, do whatever you need to do, or just eyeball it for a minute. You can convince yourself that y1 of x equals x is a solution to our Legendre's equation. And I'm going to label it LE for Legendre's equation. I know that's original. Let's say we've constructed one solution to this equation. I want to remind you from the first few appendices. Well, once we have one solution, this is a second order variable coefficient equation. I can use reduction of order to find a second linearly independent solution. And now what I'm talking about is really Legendre's equation, not thinking about imposing any initial conditions here. Okay, so think about Legendre's equation. And now I want to think about, okay, let's assume y1 of x is x. That's one solution to this differential equation. And now I want to take a page out of the first few appendices and say, let's use reduction of order to get our second linearly independent solution. If we do that, then first thing we do, don't forget, we put our equation in our standard form. So this is standard form of our second order variable coefficient differential equation. And we do that so we can get p of x. And then recall that for reduction of order, the second linearly independent solution, that's y2 right here, is going to be y1 of x times v, where v has this form that you see right here. Okay, so hopefully that's all a review. I'm going to plug and chug through that. You can watch, listen. I'm going to do it fairly quickly. I'm going to take this in steps because remember, this is pretty ugly once you get a lot of fractions in there. So first I'm evaluating the integral itself with the negative sign. And I do that with a little u substitution. Notice here, if I want to remove the absolute values from the natural log in that integral, I really need to assume that the absolute value of x is less than 1 there. Now, once I have done my u substitution, made that assumption, I can go back here and say, okay, e to the minus the integral of p of x will then, here's our e to the natural log of something equals that something again. Once we've done that, then this is the thing that really goes, oh, where does it go? It goes in the numerator of v of x. Okay, so the thing that's in the numerator of v of x is just this guy right here. All right, so I'm going to plug that in. Now v of x is going to be that numerator divided by y1 squared. Check your formula there. All right, so I have kind of this ugly fraction to work with. And again, more techniques of integration showing up here. How do we deal with this integral? Well, it turns out one of my favorites, partial fraction decomposition. You got to still know how to do those in this class. If you do, then here's what you'll get. So go off and verify that to yourself. Stop the video, go play around with it. But make sure you can do that as well. I won't give you anything that ugly on your exam. It will just be something like a hint if you need to use it. Oh, and look what I did. I did one of those things that I really don't like it when students do it. So I'm going to fix it right here. I did not put my d at x with my integral. 2 points off for me. Okay, so now once we've got our expression for y2 of x, and now we've evaluated, we've done our partial fraction decomposition and we've evaluated our integral, then here's where we get. And now I want to do a little more algebra on this thing, because if I use some log rules, I factor stuff out, I go through and do all of my sort of cleaning up things I get here. Once I distribute that x in there, here's my y2. It looks like this guy right here. And now once I have this y2 of x, I want to go all the way back. So go back to that previous video, write down what our expression was for natural log of 1 minus x over 1 plus x over 1 minus x looks like. Once you do that, then here's the series. And now I am going to distribute in that 1/2 x. When I do that, that 1/2 and that 2 are going to cancel. And look what I've got here. Got a 2m plus 2, which really, if I simplify, looks like that. Well, it turns out I'm just going to play a little game again. I'm going to be shifting my indices here. And when I shift them, I am going to shift the m inside here, shift down inside. And so what does that mean? Well, it means I shift up in the index. And so this is what I come up with. So y2 of x, you can either look at it from up here in its closed form, what we call maybe our transcendental function expression or algebra expression, however you want to look at it. Or we can look at our series expression right here. Okay. All right. So pay attention. Make sure you write these things down, what I'm telling you. Now we have two different expressions for y2 of x. Now I'm going to go back and take you through a solution, a power series solution of Legendre's equation without any initial conditions. So now we're looking for a general solution. Go back and look in your notes, because there'll be places where I just say, go look in your notes. Here's what it should look like. All right. So we'll go through that pretty quickly, and then we'll be done with this video. Now I just want to connect it all up to show you and make one point. Here's an assignment that you should do on your own. I'm kind of walking you through it here. Start with your Legendre's equation, same one as before. I've rewritten it there. I want a general solution. Okay, so I want you to go off, and here is your assignment. Find a general solution using power series. Now, we kind of did a bunch of this in class already. So look for your certain form of y, go back and plug and chug through the details. What you'll come up with are these equations, okay, or excuse me, I guess I should say this equation. And then that equation leads you to setting each of those terms equal to 0. So I get a couple of guiding equations here, here and here, and then my recurrence relation, which maybe I'll take the time to put a big old red box around. Why not? Because it's such an important thing. All right, now we have that set of information. We need to figure out what all of our coefficients are, our A sub m's. Now we don't have any initial conditions. So a big step here to pay attention to, A0 and A1, let's let those be arbitrary, because really remember, those are determining our initial conditions as well. So when you give me some, I'll be ready with an A0 and an A1 and be done. So let's start there. And if we do that, then what do those equations up there tell us? Well, I guess one point we should make right off the top is A3 is equal to 0, regardless of anything else. All right, we know that. And then A0 and A1 are arbitrary, but they're constants. So now we got to plug and chug through all those other details. Well, this is going to give us a relationship for A2. I wrote that thing down, as you can see here, arrow there to say that's how we get that equation. And now once we have A2 in terms of A0, then let's go back to our big recurrence relation. So this is our recurrence relation up there. I get A4 in terms of A2. That's m equals 2. All right, so pay attention to that. Maybe I should write that down. Okay, so this is the m equals 2 case to give you A4 in terms of A2. I know what A2 is. I go back and plug in, and I'm just giving you the results here. You should verify these. This is the m equals 4 case, the m equals 6 case. And I think that's enough cases for you to see the general pattern. I see it here, and I put it over here. All of those give us this pattern. Let's put a box around that. And this will, notice, give us all the even coefficients. And now with the odd coefficients, I really just need to go back and think about the fact that, well, A3 was 0. And once I get A3 equal to 0, as you see here, tells me, right? So go up here to this recurrence relation. That tells me A5 and A7 and all the others are going to be 0 because they're all dependent on A3. Okay, so this is all the odd coefficients. I have all the even coefficients. Let's put it all together now. Here's my power series, and I've written it down. You may have to go back and look at the notes as I'm scrolling here. A power series looks like A0 plus A1x, and then I put all of those even coefficients in. A3 is equal to 0. All the even coefficients depend on A0, and so that's what you see there. All right, so there, after I've factored out my A0, I have this expression in here. And now that might start to look a little familiar. In particular, I want you to compare it with the reduction of order form that we did before to say, oh, that expression in that set of brackets up there is nothing but my -1 plus x over 2 times that natural log term. Okay, so here we make the connection that whether we do reduction of order or we do a power series on Legendre's equation, we'll get to the same linearly independent solutions. Now, whether or not we can find a closed form for those expressions, for those series, that's a different issue. But in this case, it was easy to connect the two up so that you could see how you can arrive at this in multiple ways. All right, so I hope I've made some connections for you that these series solutions, they can arrive at our original closed form algebraic solutions when they exist, and when you can find an expression for what that closed form closed form expression for what that series is. That's another trick. Not always easy, but there are connections. We are doing really the same thing. And when we are looking at these series solutions, we're actually finding more general ways to express our solutions to our differential equations, even when we may not be able to get a sort of algebraic solution that we've been comfortable with before. All right, that's it for this video. Thank you very much for watching, and I'll see you soon.